Hi, my name is Gabby Clark, and this is my Lab 2 presentation. In this experiment, we are evaluating Newton's second law of motion, which pertains to the behavior of objects for which all existing forces are not balanced, referred to as non-zero net force. In this experiment, the net force is the vector sum of all forces acting on an object, including gravity and the drag force, or the air resistance. We will also explore the concept of terminal velocity, which occurs when the sum of the drag force is equal to the downward force of gravity, resulting in zero acceleration of the object. The setup of the lab experiment involves dropping an object, recording the actual movement, and comparing this in two models, one of which only considers gravity and one that considers gravity and drag force. I selected a concave paper plate with a mass of 13 grams and the forces in the surroundings, including earth and air. Here's my tracker video. For my observation on tracker, I set up the coordinate system as follows. The origin was the center of the paper plate, and the plate was dropped face up in a concave position. The x-axis is the positive direction to the right. The y-axis pointed up, so as the object falls, the position is negative, and no tilt adjustments were made to the axis as the plate fell straight down. However, even though the plate fell straight down, the plate was flexible enough to flutter as it fell. For coding the model that limited the force to gravity only, I used the mass of 0.013 kilograms and the end time of 0.533 seconds. The force that gravity exerts on the plate is 9.8 meters per second squared, and the other parameters are as shown. In coding the model that included both drag force and gravity, the additional parameter of drag force was added to the net force. The constant b was found by trial and error, and I determined that value to be 0.00149 so that the final output was the closest to the result from the observed tracking information. This graph shows the comparison of the two models compared to the observed tracking curve. Both models underestimated the acceleration of the paper plate since the plate was observed to fall faster and steeper than both the models predicted. The model using both drag and gravity was slightly better than the model only using gravity. It is likely that the drag / the aerodynamic forces on the concave paper plate were more complicated than the model evaluated. The fluttering of the plate, due to its flexibility, indicates that the drag was not equal across the mass of the paper plate. The concave nature of the plate, combined with the twisting of the flexible plate as it fell, provided additional forces that were not considered in the model. Rerunning the experiment by turning the plate over or crumpling the plate would affect the shape and the mass and potentially make the models align. So what does this mean? Which models, if any, predict a terminal velocity? Terminal velocity occurs when the sum of the drag force is equal to the downward force of gravity, resulting in a zero acceleration of the object. As you can see by the graph on the left, the second computational model predicts terminal velocity. This indicates that gravity is not the only force acting upon the paper plate, and by adding the drag force plays an important role on the overall net force. What if the object was initially thrown downward instead of dropped? On the model on the left, you can see that if the model was dropped, the initial velocity would be 0, and it slowly decreases in the acceleration in the end, which means it reaches terminal velocity. On the graph on the right, it shows that if the initial velocity was -10, it starts off with a really high speed, and it slows down to a terminal velocity. So, regardless of initial velocity, the object would tend toward terminal velocity in the long run. The terminal velocity is independent of the initial velocity. Thank you for watching my lab report video for Lab 2.